Welcome to the video on CMOS operational amplifiers. So it's again Bode plots of amplifiers part 2. So in the previous video we are discussing about the gain and phase margin of this third order system having three poles, having time constant tau 1, tau 2, tau 3, having three cutoff frequencies 1 over tau 1, 1 over tau 2 and 1 over tau 3. It was this happens to be omega GC where the magnitude plot crosses 0 dB, and this is omega PC where the phase plot crosses minus 180 degree line. In this particular example, omega PC is greater than omega GC, and we define the phase margin happens to be 180 degree plus the phase of the system corresponding to omega GC. So here maximum possible value of phi happens to be minus 270 degrees. If omega GC lies between minus 180 and minus 270, so this phase margin becomes negative. And if this omega GC, phi of omega GC, if the phase at frequency, gain crossover frequency is between 0 and minus 180 degree, then phase margin happens to be positive. So let us look into few solved examples of a Bode plot having different transfer function. Try to have a confidence on finding out how to find the gain and phase margin. And of course we also see what is phase margin. Phase margin is given by it is minus of the magnitude at a frequency corresponding to omega PC. So that is minus of amplitude at omega is equal to omega PC if it is in dBs. If it is in volt per volt, then it should be 1 over amplitude at omega is equal to omega PC. So at omega is equal to omega PC, if amplitude is minus 20 dB, then gain margin happens to be minus of minus 20, which happens to be plus 20 dB. So we know that this A of minus 20 dB corresponds to 0.1. So therefore GM of such system having a magnitude of 0.1 volt per volt happens to be 1 over 0.1, which is now 10. So it was said that gain margin can be written either in terms of dBs or in terms of ratio. If it is in terms of dBs, it is minus of the magnitude of the plot when for a corresponding value of gain at omega is equal to omega PC, or if you want to have it in ratios, it is 1 over the magnitude of the gain at omega is equal to omega PC. So this magnitude of the gain in this particular case is 0.1. So then gain margin happens to be 1 over 0.1, which is 10. In terms of dB, we know that 20 log of 10 happens to be again 10 dB. So both the gain margins are same. So let us see a system which is unstable in nature. So in the previous case you can see, so here gain margin is positive. The phase margin is also positive because this omega GC happens to be before omega PC. So this omega phi of omega GC will satisfy this particular condition. So phase margin is positive as well as gain margin also positive. So this is a stable system. So let us consider one more system where the system is unstable. Again we have a third order system having a pole at this point and this frequency and this frequency. You can see the slope is changing over here. This frequency you can name it as tau 1, 1 over tau 1, this is 1 over tau 2, and this is 1 over tau 3, and this is phi of this is omega GC corresponding to gain crossover frequency, and there is a phase corresponding to which is this phi of omega GC, and let us assume that this is the phase plot of that system. So if this is minus 180 degree line, so then this is omega PC, and we want to find out what is this phi of omega GC corresponding to omega GC. Now since it is like between minus 180 and minus 270, so PM happens to be phase margin happens to be negative, and as we can see now, so the phase margin omega PC is less than omega GC. The magnitude now it is positive, so A of omega PC is actually positive. It can be maybe plus 10 dB or plus 15 dB. The gain margin happens to be minus of that magnitude, so that's why it is negative. if omega PC is less than omega GC, as it is happening here. Since omega PC is less than omega GC, then system will be unstable. Let us consider one more condition where we have again a third order system. Suppose now if this omega GC and omega PCs are same, so then omega GC happens to be minus 180 degree, phi of omega GC happens to be minus 180 degree, so phase margin becomes 0 dB, and the magnitude at omega is equal to omega PC becomes 0 dB, so gain margin is also 0 dB. So a special case will be considered as an oscillatory system where gain and phase margins are 0 dB and 0 degrees. Suppose if the system is stable, then both gain margin phase margin are positive. In the previous case we saw that if it is unstable, both phase margin and gain margin will be negative. So this is a summary. Order of the system, if it is 1, so here it is a double star, given that without any finite zeros. So we are considering all the zeros are at infinity without any finite zeros. If it is a order 1 system, then we call it as an absolutely stable system if it is there towards the left side, if the pole is there towards the left side. If the poles are there towards the left side, and if it is a second order system without any finite zeros, then also the system is called as absolutely stable. If the poles are there to the left side and if the order of the system is 3, so it is conditionally stable. But if the value of k exceeds a certain value, then the system may become first oscillatory and then become unstable. So this is now again in terms of gain margin, phase margin. If the phase margin is positive and gain margin is also positive, in terms of ratio it will be greater than 1. So then the system stability is it is more stable. It is stable. So that corresponds to omega GC greater than omega PC. So this is for a third order system. If the phase margin is negative and if the gain margin is okay, let me see. This should be negative. Let me make that correction. Suppose if phase margin is negative for a third order system and gain margin also negative, which corresponds negative in terms of dBs, which corresponds to a ratio which is less than 1, then we call system as unstable, where of course this is actually omega PC. Omega PC will be greater than omega GC. So let me make that correction now. Okay, we shall make this correction now. This is omega PC will be greater than omega GC. And if the phase margin is 0 degrees and if the gain margin is 0 dB, which corresponds to a gain margin of ratio 1, then we're going to have the system will be oscillatory in nature, which corresponds to a condition where omega GC equal to omega PC. So system will be stable, unstable, oscillatory. So if both gain and phase margins are positive, then the system will be stable. If both are negative, then the system will be unstable. And if both are 0, 0, then the system will be oscillatory in nature. So let us consider a few examples of Bode plot and try to obtain its gain and phase margins. Now here we have a second order system having poles at 10 and 100. So we have the magnitude plot given by magnitude equation is given by 20 log of 100 minus 10 log of 1 plus 0.1 omega whole square minus 10 log of 1 plus 0.01 omega whole square, and the phase happens to be minus tan inverse of 0.1 omega and minus tan inverse of 0.01 omega. And we'll write the magnitude and phase for different omega values, which is over here. If omega is equal to 0, magnitude is 40 dB, the phase is 0 degrees. So likewise it was found out for different values of omega, both magnitude and the phase. And a particular frequency was found out where the magnitude happens to be 0 dBs. So that corresponds to gain crossover frequency, which is in this particular case 308.3 radian per second. And since we know that since it's a second order system having only two poles, the omega PC is at infinite, because we're going to get only at infinite radian per second. The phase happens to be minus 180. So this omega PC is something like infinite radian per second. So corresponding to omega GC of 308.3 radian per second, we have the corresponding phase as minus 160 degree, which happens to be pi of omega gc. So corresponding amplitude at omega is equal to omega pc is actually minus infinity dB. So phase margin is given by 180 plus phi of omega gc. In this case, it is 180 minus 160 degrees, which is 20 degree. So gain margin is minus of the magnitude at a is equal to at omega is equal to omega pc, which is now minus of minus infinity, which is infinite. So since gm and pm both are positive, the system is stable. So let us consider second example where the transfer function is given by 200 divided by 1 plus 0.2s into 1 plus 0.01s into 1 plus 0.04s. The time constant of the poles are 0.2, 0.01 and 0.04. And we have the magnitude equation given by this, and this is the phase equation. Similarly, as we found it in the previous case, we can obtain the values of magnitude and phase at different values of omega and find out what is omega gc and omega pc. So that's what we are trying to find here. So this is different values of omega and their corresponding magnitude and corresponding phase. It is interesting to note that at a particular frequency, which is omega pc, the phase happens to be minus 180 degree. So this is omega pc, that is 55.9 radian per second. So as we keep increasing the frequency, at 124 radian per second, the magnitude becomes 0. So this happens to be omega gc. So since omega pc is coming earlier compared to omega gc, so in the previous we have found that the system has to be stable. So let us verify it. Omega pc is 55.9, whereas omega gc is 124. The corresponding phase at omega gc is minus 217 degrees. Now the system has to be unstable. So that's what we found in the previous case. So since omega pc is coming earlier to omega gc, system has got a phase of minus 217.4 degrees. So PM happens to be 180 plus that phase, that is 180 plus of minus 217.4 degrees. This happens to be minus 37.4 degree. The corresponding gain margin is, that is at omega is equal to omega PC, we have 16.05. So it is minus of 16.05. So gain margin is also negative now. So since phase margin is negative, gain margin also negative, the system is unstable. So let us see one more example where we have again three poles. There is a pole at origin, and there is a pole at with a time constant 0.1, and there is a pole having a time constant of 0.001. This is the magnitude equation, this is the phase equation. So this minus 90 degree corresponds to the pole at origin. We have minus tan inverse of 0.1 omega corresponding to the pole at 0.1 as the time constant. So we can directly find omega gc by equating this magnitude to 0. Upon equating this magnitude to 0, we'll get omega is equal omega gc happens to be 21.26 degrees. Upon substituting that frequency onto the phase equation, we get the corresponding phase, which is phi of omega gc, which happens to be minus 156 degrees. So let us also find out what is omega pc. So omega pc can be found out by equating the phase equation to minus 180 degree. So equating this phase equation to minus 180 degree and using the calci, we can do alpha. Of course, we can do shift solve twice. So we're going to get omega pc directly as 110 radian, 100 radian per second. The corresponding magnitude, by substituting this omega as 100 in the magnitude equation, we get the magnitude as minus 26.10 dBs. So as we know that this is phase and this is the magnitude, we can find the gain margin and phase margin. So gain margin and phase margin happens to be 24 degrees and 26.1 dBs. The system is stable. So this way we can directly find the the phase and the gain margin. This is the next problem. We can have a look at how